Hi, my name is Claire Xiao, and this is my lab report for Physics 2212, Lab 4, Macroscopic View of DC and RC Circuits. As an introduction to Lab 4, the purpose of this lab is to do the following: understand and predict the behavior of circuits that are in series and parallel, measure conventional circuit and potential difference using multimeters in the circuits, and observe how ohmic and non-ohmic resistors and capacitors behave. Then we model using CCK certain circuits with different components to explore their impact and behavior. And finally, we model the time-dependent voltage across a discharging capacitor to compare theoretical and experimental values. The results are shown above. Theoretical was 6 seconds, and the experimental results were 5.995 seconds. As an overview of the physics principles used in this lab, Ohm's law, conservation of charge, loop rule, EMF, and node rule were the primary physics principles, and they are described in detail beneath each of the respective principles on the screen. So the initial predictions of currents I1 and I2. So the calculations to predict these currents that would be measured by the two ammeters. So as you can see the calculations above, and the final result was 0.0204 ampere. So the CCK model results, as you can see in the figure above, this is what it looked like when you modeled it in CCK. Two 1.5 volt batteries are used, and one 47 ohm resistor and one 100 ohm resistor are used. And the simulated result was equal to 0.02 ampere. So this is the CCK model result, but backwards. Basically, the wires were connected from the input to the output and switched. And then when the ammeter is connected backwards, the results remain the same at 0.02 ampere. So CCK model result inserting a voltmeter. When the voltmeter is inserted, the ammeter reads 0 ampere because the circuit is no longer closed. It's now considered open. And the voltmeter reads 3 because the potential difference between the two nodes on the voltmeter is being measured. And as you can see, that potential difference calculation yields 3. So measuring potential difference, because of the loop rule, the total potential difference should be 0, and the calculations are shown above and highlighted. You can see that that does hold true because the circuit is steady state, that the total potential difference is 0. And here's the potential difference graph. You can see all of those potential differences and the corresponding bars that were added to the graph. Here's the CCK model result for the ammeter and resistor in parallel. When the ammeter is placed in parallel with the 100 ohm resistor, the reading increases from 0.02 ampere to 0.06 ampere. The ammeter displays a lower resistance than the 100 ohm resistor because the current flows through the wire as it is the path of least resistance. And doing the calculation for this, doing 3 volts over 47 ohms yields 0.063 ampere. So calculating resistance, you can see the results that are highlighted in yellow, but basically these are the readings that were from previous slides, and you can see each of the results listed above. So moving on, here's the RC circuit that was built in CCK. When a 10 ohm light bulb, a 9 volt battery, and a 200 capacitor are connected, the battery will charge the capacitor and light up the light bulb. And you can see when just the light bulb and the capacitor are connected, the light bulb is initially bright, and as the capacitor discharges, the light bulb slowly dims, and the current eventually reaches 0. So the capacitor charging and discharging times, the 10 ohm light bulb you can see below the two figures that are on the bottom left side of the screen. It was a 16.1 second charging time and a 19.9 second discharging time. And in the 20 ohm light bulb, the charging time was 30.3 seconds and the discharging time was 39.9 seconds. And finally, the time-dependent voltage across a discharging capacitor. So this is the Excel screenshot, which is graphing the natural log of delta V over delta V initial versus time. And so experimentally, you can see the equation there and the slope for that. doing 1 over the slope is equal to 5.995 seconds, which is how I obtained my experimental value, and the theoretical value multiplying the ohms together, you get 6 seconds, so that was extremely close. Finally, the report and conclusion questions. First, what if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? So actual ammeters have some resistance, therefore the current would have a lower value than the simulated one in this lab. Because current and resistance have an inverse relationship, so if the resistance of the actual ammeter was higher, then the current would be lower. And finally, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the current circuit? What would happen from this is the capacitor would charge slower because of resistance that real-life batteries experience. The CCK assumed that the capacitor would charge far quicker than would have occurred in real life.